thank you for the organizers to organize this nice school and to see this room of students, and postdocs and researchers. And yes, this is the outline of my talk. I will go very quick on the recap of what you have heard in the previous slides, in the previous lectures about the G0 W0 simulation. Then I will move on to the problems that may arise when you try to apply GW calculations, G0 W0 calculations to large systems, and we will define what large system means and how we solve those problems. So we try to solve as many problems as we could. And finally, I will try to extend also a little bit, give you an overview of the latest developments about the use of GW, not just describe charged excitations, but also neutral excitations, and specifically to develop an embedding of a high-level theory for configuration interaction in EFT, from in-field theory. So why do we care about charge excitation? Not just because we want to simulate photoemission or inverse photoemission experiments, but we would like to predict the electronic structure of several systems. Here you see there is a simulation box where there is a nanoparticle, and the nanoparticle is actually made of two compounds. And here you see the valence band, and then the gap, and then conduction band spatially resolved. And you would like to predict the band offset, so how the valence band and the conduction band align between the two systems, because you want to use the system for energy conversion applications. Here you have a crystal, silicon, and an amorphous system, silicon nitride. You have an interface between the two, and you cannot reduce this interface to a small unit cell because you want to describe the amorphous system here, and you want to have enough atoms so that you describe the interface, not just a unit cell made of silicon and silicon nitride. And this is the, again, valence and conduction band of the two materials for energy conversion applications. Here, this is a silicon carbide, the 4H polytype, and you see there are two atoms missing here. This is called a divacancy. And this point defect has the property to attract an electron. It creates a defect state, and we can predict, oh no. Okay, so we can predict the position of the energy level associated to the spin down in blue and the spin up states in red. These states fall within the energy gap of the material. So band gaps, band offsets, different position of different levels are important. And in all these systems, you have to describe thousands of atoms just because the system is complex, it is heterogeneous, and you have valence electrons. So you may have up to 10,000 valence electrons. So this is large systems for this for this method. Okay, so we saw already that so for this large for this size of the system, DFT would work very well. But the accuracy of the Kohn-Sham energy levels is not good enough, as you heard already. The energy gaps are severely underestimated by DFT. This is an experimental energy gap versus the theoretical energy gap of several materials. Every dot is a material. And you see that whenever we are on track, we are hitting this line, and GW can do that, but DFT cannot. And so one has to move from the density and a potential functional of the density. This is from DFT. One has to go to Green's function and the self-energy. And that's many-body perturbation theory, as you heard. From the Green's function, one can extract information about the electronic density, the probability of particles to propagate, and also, as you heard from the previous talk, Claudia's talk, the poles of the Green's function correspond to the excitation energies of the system. So the energy that the system has when you remove or add an electron. That's the Lehmann representation of the Green's function. And this is the definition. So to get to use this method, then you have to set up an equation of motion for a single particle Green's function, and after long derivation, where you have to derive with respect to time the step function present here and the field operators using this commutator, you end up with this equation of motion. So to know the single particle Green's function, you have to know the two-body Green's function, and so on. But to know the two-particle Green's function, you would have to know the three-particle Green's function, four-particle Green's function. So there's an open form of equations where you cannot know the single particle Green's function until you solve all the many-body Green's function. So to close this form, then we define the self-energy. Now we only have an equation for the Green's function, the single particle Green's function, and we have hidden all the many-body physics in the self-energy, as you heard this morning already. So then if we apply this, the previous equation to the Lehmann representation of the Green's function, we get an equation for the amplitudes of the Lehmann representation of the single particle Green's function. And we have the excitation energies, the poles of the Green's function. So this equation resembles very much the equation of Kohn-Sham DFT, where we solved for single particle wave functions, and we had here the function of the density. And here we had the Kohn-Sham energy eigenvalues. So one can set up a perturbation theory to start from DFT energies, correct them using the perturbation, so the difference between these two Hamiltonians bracketed on Kohn-Sham states. And this correction has a real part, so it shifts the energy, as Claudia said. And also there is an imaginary part that gives you lifetime, so we have quasi-particles. And of course, this resembles photoemission and inverse photoemission, because this is the experiment where you remove an electron, you add an electron. And later on, we will see that the GW is a key step also for the derivation of neutral excitations, where the system just promotes an electron, but doesn't change the number of electrons. So the electron doesn't escape from the system. Okay. So Hedin wrote this paper in 1965, and there is a nice statement here, a humble statement at the end of the abstract that we don't see probably anymore in the papers nowadays. He wrote, there is not much new in principle in this paper. The emphasis is only on the development of numerically manageable approximation schemes. And so this is actually what opened the field back in 1965, and it was only in the 80s where this was applied to materials starting from DFT. So you heard that for the self-energy step consistently we need 5 equations, and the GW approximation, the G0 W0 approximation is actually removing the subconsistency and also skipping the calculation of the vertex. That's the definition of the approximation. Okay, so now we want to apply this technique to large systems, and I will review problems that may arise when you want to treat thousands of atoms at this level of field. So if you think about Hartree-Fock, in Hartree-Fock, the particles interact with a bare Coulomb potential, 1/100. And in Fourier space, if you take the Fourier transform of this, it's an analytical function, and it's actually a diagonal matrix. So the plane waves are not mixed. You only need to store the elements along the diagonal. But in GW, the quasi-particle interact with the screened Coulomb interference W. This is what gives the name GW. And it's a non-local operator, just because there is screening in the material. So the screening makes this could be non-local. And there is also retardation. So we see frequency here appears. One can still take a Fourier transformation of this object, and you have now a full matrix. So a big matrix that is no longer diagonal. just because the screening of the material can couple the off-diagonal elements of this matrix. This means that the perturbation with a given energy can couple to a response with different energy. So let's take, for example, liquid water, so H2O. This requires a grid with 256 points in real space. So we have a three-dimensional system, and each axis is sampled using 256 points. And so we have millions of elements for R, millions of elements for R prime. And so this matrix in real space requires 4 petabytes of memory just for one frequency, which is quite expensive, petabytes. So if you take the Fourier transformation, you can reduce this to 1 million of elements. This is the order of plane waves that you use in density functional theory. Million of plane waves for a big system. 1 million by 1 million matrix takes 16 terabytes. Okay, so each element is a complex number, and I just multiply 1 million elements by 1 million by 16 bytes. How big is it now? One complex number. 16 terabytes just for one frequency. So one cutoff is needed to reduce the size of the matrix because we cannot really play with these matrices. So typically then a physical approximation is introduced, and one say that the system only screens low energy perturbations. And so you order the plane waves according to the kinetic energy. So you start ordering them with the low kinetic energy and high kinetic energy, and then you take just one chunk, the first chunk of the matrix, the one that corresponds to implementing a cutoff, okay, for the response function. And this reduces the size of the matrix to arbitrary size. For example, 50,000 by 50,000 takes only 440 gigabytes of memory. So this is what will, I think that the talk that was supposed to be now will explain the cutoff, and you will hear it after my talk. But so let's now think about it in a different way. And you have a full matrix if you have access to the eigen decomposition, so eigenvectors and eigenvalues of this matrix. So this is the eigen decomposition, eigenvector and eigenvalues. Then you can, in a spirit of principal component analysis, you can retain only the most important eigenvalues of such matrix. You would not need to implement a cutoff in the plane waves. So you retain the full plane waves that DFT was started with. You would have to implement a cutoff in this principal component space, in this eigenvalue space. And as I will show you, the eigenvalues converge to 0 very quickly. And so one can reduce the size of the matrix to 1,000 by 1,000 elements, which corresponds to 16 megabytes. So we started from petabytes. So this is called a low-rank representation of the composition of W. Okay. So, okay. I told you, if we have access to the composition, then we can use it. But what is the cost of getting that diagonalization? So we need to use a linear response to get the diagonalization. And so this is the starting point. This is an equation. These are the equations that you saw in Claudia's talk. We have the screen Coulomb interaction and how it is related to the bare Coulomb interaction. We can either express it using the full response or the irreducible response. So if one symmetrizes the response function, so you just multiply by the square root of the Coulomb potential, just because you want to then feed this into a diagonalization solver. So you symmetrize this operator, then you get this relation between the full response and the irreducible response. So it's just linear algebra. You need to invert a matrix and multiply by another matrix. So if you have access to this decomposition, this eigendecomposition of chi-naught, the matrix inversion operation becomes easy, okay? So you just need to invert and work this function on the eigenvalues. Okay, so the first way to get to the decomposition is to store the full matrix, right? We compute this chi-naught, the reducible response, using the so-called Adler and Weiser formula from the 60s. And this is actually, this formula can be derived once you take the GW approximation, and so you remove the vertex here and you get the bubble diagram that in the previous lectures you saw many times. So there is a summation over occupied states, a summation over unoccupied states. This means that it sums over all possible ways of exciting one electron from valence and putting it to conduction. So you need to access not just all the valence states, but also, in principle, all the empty states. And the only thing that, the only factor that really helps you in truncating this summation over unoccupied states is this 1 over the energy difference. So whenever the energy difference is too large, then the contribution decays. Okay. So you can start by setting up this problem and then diagonalize this matrix. But there are 3 problems that I colored here. So first of all, in blue, we see that this matrix is too large and we cannot diagonalize it. If we use Fourier space or even worse, Dirac space. Then we have an open summation over empty states that sometimes it's difficult to converge. And we have the frequency. So we should do this for every frequency in a grid, because then we need to integrate over frequencies to get GW. No. So this one is not amenable for a diagonalization problem. We must go back to the definition of the response, which is how the density changes when you apply a perturbation to your system. In a way, this is similar. So this is written in Green's function, and this is written in a imperative, the definition of the response, variation of the density when you apply a perturbation. So if we think about that, then we can apply a perturbation. This is the perturbation, and then the perturbation changes all the orbitals, because once you have a perturbation, your Hamiltonian gets an extra term, and so you have the eigenvectors of such a Hamiltonian are different from the eigenvector without the perturbation. This leads to a variation of the density. You measure the density, and then you take the ratio, you get the description of the response function. So if you follow this approach, you do not need empty states, because to get the variation of the density, the linear variation of the density, you just have to sum over occupied states, and then you have unperturbed states and the perturbation of an occupied state. And you can use perturbation theory, okay, to know how a function, a wave function, changes when you have a perturbation. This is a formula that is taken from quantum mechanics 101. And if you make it a slightly, if you write it in a slightly more complex way, you get the Sternheimer equation, which is this one. And this is the unknown of the problem. This is the Hamiltonian of Conchamp. And here you see there is a projector over all the empty states. And you're going to use the fact that the eigenstates of the Hamiltonian form a complete basis set. So if it's complete, summing over all the empty states is exactly the same as taking the identity and subtracting a summation over occupied states, just because the sum of the two should be a resolution of an identity. So now you can, this is a matrix. Oops, sorry. This is the matrix. This is an unknown. This is the known term. So AX equals B you're going to solve a linear system with a preconditioning logical gradient method. And you can do this also with frequencies, finite frequencies using the Lang's algorithm. And this is at the base of density functional perturbation theory that you see in the reviewed in this review Modern Physics from 2001. This is what's used in the 2000s to get phonons. And then at that point, the perturbation was a displacement of the atomic structure. So we can get then the response function without the need to get empty states. Okay. Then we're going to use an iterative diagonalization method to diagonalize the electric matrix, and we can diagonalize either the irreducible response, okay, so either on the left, or we can follow the strategy on the right, which is the diagonalization of the full response. The difference between the two is actually what is known in chemistry, quantum chemistry, as the uncoupled perturbed Kohn-Sham equations and the coupled perturbed Kohn-Sham equations. So in the strategy on the right, you have an extra loop that changes the parts of the Hamiltonian that depend on the density. For instance, the Hartree potential depends on the density. If you computed the response of the density, you would have to update that potential and then solve consistently the response of for the density. The strategy on the left is more practical because you don't have this extra loop. You just have perturbation, evaluate the response of the system using linear response without empty states, and then represent have a representation of the response function in a reduced space, a direct representation. And then you can converge to the eigenvectors and eigenvalues of such a matrix. These are the eigenvalues. And they start from, this number is very small, so this is a negative number. And here we have 0, so they decay towards 0 from below. But at some point, they are very small, and this is what justifies the truncation. So you can stop here, for example, and you get the principal components of this matrix. So this is an iterative technique. You start from a gas, random potentials, and you get closer and closer to eigenpotentials, so potential that diagonalize the response function. Once you have the access to chi-naught, then an easy inversion here gets you to the full response function. And so the strategy on the left is totally equivalent to the strategy on the right, but you skip the coupled perturbed Kohn-Sham equations thanks to the fact that you apply the Dyson equation. So what are we doing here? We are using a Davidson algorithm to diagonalize the electric matrix. This is the same algorithm that you use all the time when you solve the FT, because you use Davidson to find the most important eigenvalues, eigenvectors of the Kohn-Sham Hamiltonian. Okay, so in a way, this becomes more similar to the FT because you would have to diagonalize iteratively a matrix. Now the matrix is the response of the system. So strategy so you have your full matrix strategy on the top, define a cutoff, the kinetic energy cutoff. This scales quadratically with the system size, and it scales as quadratically with the plane waves times the number of unoccupied states times the number of occupied states. The strategy at the bottom that I described so far, the one where we have a eigendecomposition of the full matrix, still scales quadratically because we see 4 times n, but the prefactors are smaller because now the number of occupied states is much smaller than the number of unoccupied, number of empty states, and the number of eigenvalues, so the number of perturbation, is much smaller than the number of plane waves, thousands versus 100,000. Okay, so we have also reached a separable form for this matrix, which is important for scalability. And this is also, we can easily apply the full frequency integration for GW. So this is the self-energy, and you need to compute to evaluate this integration from minus infinity to plus infinity. So from here to here. So in using Cauchy theorem, you invent this contour deformation technique, and you just have to evaluate this integration along the imaginary axis, where every both G and W are smoother because you are falling away from the poles of these objects, these functions. And you just have to track the poles that eventually fall inside your contour. And this integration is actually efficient when you represent the response function on the principal components. And so you represent the direct response using the eigenvectors of the reducible response. You can actually you can actually diagonalize just the response at omega equals 0, so a static response, and use those eigenvectors to represent the response at any other frequency. We've checked this approximation. Of course, the matrix is no longer diagonal, but this is a low-rank representation, so it's 1,000 by 1,000 matrix. Finally, you can use the Langschus algorithm to get information about the frequency dependence here in an iterative fashion and for many frequencies at once. Okay, so all this starting from DFT, done performed with quantum espresso, and then the decomposition of the dielectric matrix, and then the contour deformation, and then quasi-particle energies, is actually not implemented in YAML, not that I know, but it's implemented in a code called West that is interfaced with quantum espresso, and it has this benefits, the benefits of not using empty states, the fact that there is a full frequency integration, and there are parallel iterative techniques for to help you speed up the calculation. So the West code was designed to tackle problems, large-scale problems, where you don't have many symmetries. So if you look for, if you're looking for solutions to problems where you have k points with symmetries, then this is not the strategy that you want to use. But if you have a large system, potentially an amorphous system, or a system with very few symmetries, with lots of atoms in your simulation box, then this pays off. Okay, so in the code West, actually, it scales well on GPU nodes. So this is GW. This is the most expensive calculation, actually, out of the other ones. So we have embedding calculation, BSC, and 3DFT. And this is the 5 minutes, 30 minutes, and 3 hours using this many number of nodes on a machine that has 4 GPUs per node, such as the one that is available, for instance, in Italy, in Cineca, and there are similar other machines in Europe. So this is now, these are the 3 systems that I showed you at the beginning, and this is the local density of state at the level of GW. You see that the energy gap has been opened by the presence of GW. And this is the count of the number of atoms, number of electrons, so 10,000 electrons, number of plane waves. When I told you that there are millions of plane waves, these are the number of plane waves in DFT, and also number of spins. Okay, so fine. So in the last part, I will, it will have 5 minutes. Yeah. Okay, so I will use GW to describe not just the charged excitations, but also neutral excitations. And I will introduce an embedding. So we want to combine 2 levels of theory. One very expensive, which scales factorially. So full configuration interaction with DFT, which is good for covalently bonded systems and scales cubically. And the motivation for doing so is, for example, if you want to study a defect in a material, this is a system that is important for quantum information science, because So this is the conduction band for resistance of diamond. This is the valence band. I just plot them. I drew this by hand, so this is not a simulation. This is the defect, dB in the energy gap. For instance, a defect made by the presence of a nitrogen next to a vacancy. And this defect actually has a triplet ground states, and 2 states can be used to store quantum information. So one state and then the other state. So you have a qubit in our material. And then you need to excite it in order to read this, this system. And it's important because you can do the initialization and readout optically. And compared to all the other qubits available, it works at room temperature. So this is the pro of this system. And it's compatible with semiconductor technology. So one sees, so the field sees this as a way to take the semiconductor technology and make it quantum. So for this lecture, so what are we interested in? We are interested in transitions from ground state to an excited state of the defect. The electron was not able to escape from the system. Okay, so I'm just reshuffling the electrons so that now I'm occupying an excited state, but note the number of electrons did not change. So we are not falling in the perfect scenario for GW, because in GW we extracted the electron. And so this is the simulation box, this is the defect, so the NV center in diamond, and this is the ground state, triplet excited state, singlet excited state. So we would like to express the excitation as a linear combination of all the possible ways to remove an electron from valence and put it in conduction. You will hear tomorrow that this is done with TDDFT or accelerator. But we also want to have double excitation. So why don't we remove 2 electrons from valence and replace it in conduction? Why not 3? Why not 4? And so why not n? So full configuration interaction. Okay. So of course we cannot solve full configuration interaction for the entire system. That is a challenge, maybe with a quantum computer in the future, who knows. But as of now, we cannot. What we can do is to solve the full system with DFT, but DFT sucks really at giving you these energies. So why don't we embed the 2th level of theories, full configuration interaction in DFT? And we use full configuration interaction only for a reduced part of the system, for the active space, the defect. That's because all the physics that of interest is here. Okay, so the 3 steps for this, you start from DFT, typically done with quantum espresso. Then you define an active space, I will define in a moment. So you select relevant quantum states. Then you define an effective Hamiltonian that describes these excitations. And then you can solve it using an ITRF solver. So you find the ground state and excited state. Or also, using a quantum computer, you will get the same effect. So this is full configuration interactions. Okay, so this is the 3 steps. And the effective Hamiltonian is made of a 2-body term, so 2 particles interact, and also 1 particle feels a potential because we come from DFT. And the complexity here is to design a double counting scheme so that we don't count the interaction twice. There are interactions that we would like to count them with full configuration interactions. Hartree, for example, can be left at the level of DFT. Described with DFT. So how do we pick the active space? We take all the quantum states, we measure how well they are localized on the defect site. So we integrate over a volume. So if we integrate over the full cell, we get 1 because the states are normalized. If we integrate the norm. If we integrate only in a sphere centered on the defect, then we get a measure on how well the state is localized here. So we get the most localized states, and we put them, we rank them, and we take more and more states, and then we see convergence of the excitations. So this is how we pick the active space. And Now GW plays a role in defining the Hamiltonian here, because the two-body term now need to take into account the fact that the two electrons are not interacting using with a bare Coulomb interaction, because the remaining electrons that belong to diamond are screening the interactions between the electrons that belong to the leaf. Okay, so we take this equation where this was written before as I naught. Okay, this is the connection between the screen Coulomb interaction and the bare Coulomb interaction. This is what we saw in the first part of the talk and also in the talks before me. And this is the bubble diagram. But now we identify Green's functions for the active space and the rest of the material. And we are able to define a response of the rest of the material and excitation that only belongs to the active space. So this is called effective Coulomb interaction potential constraint RPA approximation that we did not derive, but actually this was derived in 2004 by the MFT people. And now, so it's clear what we use as two-body interaction. Okay. And now we need to work on the one-body interaction because we have to perform the same split between the self-energy. Now we have DFT or DFT, as we will see GW as low level of theory. Then we have a high level of theory that done with full configuration interaction. And we must introduce a double counting scheme so that we don't count twice the Hartree, the exchange, and the correlation interaction. So Hartree, we want to describe it with DFT because we don't want to screen the Hartree interaction. So we remove it from full configuration interaction. And for the exchange and correlation, we must remove it from DFT. But it's very difficult to define the exchange and correlation potential for a subsystem, for a part of the system. Not easily separable, this functioning. And so one introduces DFT plus GW as the low level of theory, because now this allows to define a self-energy just for the active space. And so this is the key approach, the key development in order to design a double counting scheme that is robust. How robust? We see it here. So this is the experimental value for the triplet excited state of the Young center. This is the double counting scheme. So we have DFT plus GW here, full configuration interaction minus a double counting scheme. And so if we use GW, then we get a number here that resembles experiment and does not depend on how we started DFT. And whereas if we use other techniques such as Hartree-Fock double counting scheme incorrectly applied to DFT, then we get results that are not correct and depend a lot on the starting point. Okay, so now we can do also comparison of this level of the full configuration interaction with the TDF that you will hear tomorrow, just because now we have access to the double excitations. So this is an ongoing work. And also the role of the hybridization of the defect with the environment, and we have work in progress here. So it's important that you think that in a code you can have all this method implemented with the same numerical techniques, because now you can make a fair comparison between the theories. And more recently, we are using the many-body states to set up a Fermi-Golden rule approach to describe the rate for intersystem crossing to appear. So to switch from a triplet state to a singlet state, so to change the spin here. And this is an important quantity that is needed in order to use the defects for quantum information science. And here we have a comparison between theory, the blue line, and the experiment performed at Argonne National Lab here. So they are on top of each other in this region, and here there's a mass, and we have to figure out what this mass means. This is an archive paper. Finally, I want to say that you don't want just to describe multi-configurational excited states, but also you would have to relax the system in an excited state. So you need to access forces for excited state energy. So because once you shine light on the system, then the system rearranges, so the atoms move, and you would like to compute forces for excited states, and we have access to them by using TDDFT with and without spin flip in this code. Okay, so concluding by saying that, so G0 is a powerful approximation to the Adian's equations. Originally, they describe charge excitation, but as you saw, they constitute the key step also for the derivation of quantum embedding theory to describe neutral excitations. And as you will see tomorrow, also neutral excitations within TDFT and BSC. And iterative diagonalization methods can improve the applicability of GW to complex heterogeneous systems with thousands of atoms in the simulation box. So I would like to thank the collaborators, Giulia Gallo in Chicago, Professor in Chicago, Peter Yu at the developer at the National Lab, the computational facilities where I ran the simulations, mostly Cineca in Italy, in a machine called Leonardo, and the funding agency. Thank you.
So we have a
question.
Time for that.
We introduce orbits into magnetic systems and can create a spin defect. In that case, we check that electrons need to be present for both spin up and spin down channels to realize potential applications for quantum information science. Or do we have, is it okay to have half spin channels? It's fine.
You need to have a spin polarized calculation. You need to take care of spin up and spin down. And if you want to describe intersystem clocks, you also need to take care into account spin orbit effects. Yeah.
So the electrons for to excite the electrons, so we need for both spin up and spin down channels.
Yes, you need to take care of both.
But it is okay to achieve the magnetic state, right? So when one spin up channel can have a different band gap compared to the spin down channel, is it relevant?
So are you asking, is it okay to excite only one spin channel and not the other?
Yes. It's like I'm looking into the analogy of digital binary logic of ones and zeros. Spin up channel we can excite to a certain energy, whereas the spin down channel we can excite to a certain different energy. Is it possible to look into it like that?
Yeah, you can do that, but yeah, in principle, to excite the whole system. Sure, because how you can excite just one. We mean magnetically.
Yeah.
I did not work with magnetic systems, so perhaps it's possible, but I have no experience with that.
In your opinion, what is the ideal case? How would we achieve in this scenario?
I actually don't know. I need to think about why don't we talk over lunch of this? Yes.
Just making the difference between organizations, even high level, we have the stuff back to the society and we over the really right. Thinking, I guess, how much is that going to have
Right. So when you solve this problem, actually, when you have the second quantized Hamiltonian, you start solving it with a full with an iterative diagonalization like Langshaw's. And so you get the eigenvectors like the values of this matrix, second quantization. This is equivalent to having a self-energy that describes the interaction between the electrons among the active space. Note that these summations do not run over the whole system, but only for electrons that belong to the active space. So you can define a self-energy associated to this, this effective Hamiltonian. And so you want to use that self-energy for the exchange correlation, but not for the heart rate, because the heart is already described at DFT does. So yeah, from DFT, you need to subtract exchange correlation because this is what you don't want to have, because it is what led to the problem of the band gap being severely underestimated. But you don't want to screen the heart rate because the heart is already taken care by DFT. So you define the double counting scheme to subtract exactly. So if you take this summation, then you see that the heart rate in the heart so cancels out with the full configuration interaction heart, and this exchange correlation cancels out the DFT plus GW. So it's by design. This is what we want to do, and this is the outcome of how we define the double counting scheme. I don't know if I answer your question.
The active space.
Yeah.
Is which level you count the configuration interaction.
The active space is
What level you use?
what level I use for configuration interaction. Which level? Sure. How do we select the active space? So it's a set of Poncham states. So from DFT, you have Poncham states. You have many, all the occupied ones and empty ones. You cherry pick the Poncham states, and you form a subset of your Poncham state. That defines an active space.
But so when you discuss the level, when you take out the small sample for the IPG price, then you said that you select the first variable one bunch of eigenvalues. So I was wondering, usually the small sample that maybe the one eigenvalues, which are the values in the natural transition, but then the screening is dictated by the random variable screening, by the higher level. So isn't the issue to select the first 1,000? Isn't there the risk of mixing with the data frequency?
So first of all, when I said 1,000, of course, is to give an idea, and every system you need to check. So it's a parameter that you would have to converge. Actually, the energy of each, so I don't think you can associate an energy to an eigenvalue because in reality, so an eigenvalue to an eigenvalue corresponds an eigenvector, and an eigenvector is a little combination of many plane waves. So if you want, you can compute the mean kinetic energy associated to an eigenvector, and you will see that perhaps the lowest eigenvalues will have a lower mean of this kinetic energy, but not zero. So you still capture plasma also with the small eigenvalues. So it's not a truncation. This is not an energy space, right? So you keep the full plane waves, so you have the full kinetic energy, but just mathematically you only cherry pick the principal components of this matrix. So it's a single value decomposition. Yes.
Yeah, and I don't know if I completely understand this, but I think that you are using DFT as the reference function, and then from there you are doing installations and then you're doing interaction, right?
Yes.
What happens, and then you remove the correlation effects from DFT, but what happens when you have a degenerated state at the beginning and something like DFT can like
Yes.
struggle a little bit, then the other excitations are some kind of pressure.
So everything I said assumes that so everything. So in practice, when we apply many body perturbation theory, then we start from DFT. So if we cannot solve the system with DFT because already the ground state is strongly correlated, then we don't have a starting point. At least I don't have the starting point for the improvement. The DFT doesn't have to be perfect, but it needs to be able to describe the physics not in a quantitative way, but at least qualitative. It should be good. Okay, so if DFT cannot be used for the ground state, then I must change completely workflow. I need to use a totally different method that starts from the beginning with strong correlation.
But at the end, the result, I mean, you even feel skill at the end of the good, no?
As of now, this should be the good starting point, okay, yeah. And then we correct it. And then the art is about how to correct it, yeah.